My name is Roy Dekker. Been working here at Precision Electric for about 34 years, been in the trade for a little over 40, and class today is on troubleshooting electric motors in the field. So starting off in the first section there, basic troubleshooting tools that everybody should have is a good DC megohm meter, preferably a 1000 volt megohm meter with 2K plus 2K scale on it. A lockout tag out kit, which is very important. You want to make sure that you lock and tag out your energy sources before doing any troubleshooting. A volt ohm meter, a clamp on amp meter, tachometer, and your basic hand tools. In the first section there, it shows, in case any of you guys don't know what an electric motor looks like internally. I mean, we do have some sitting around here, but if you haven't seen them before, there's some references for you. Just give you an idea of some of the nomenclature, what to expect inside a motor. I know when I started in the trade, I'd never seen really inside of a motor before. I didn't have a clue what was in there, but once you get into them and open them up, there seems like a lot of parts at times, but it's just really pretty basic. A lot of different things in there can cause you problems. You can have electrical problems in the motor, you can have mechanical problems in the motor, you can have both of them. So just things to be aware of. There's examples of oil-filled motors with Babbitt bearings, there's ball bearing motors, etc. One thing we find in the field a lot is improperly taped connections. It's very important that you properly make connections properly and tape them properly. I'm going to hold that up. We don't need to tape it yet. Basically, you're going to have leads coming into your motor from your supply, and then you're going to have motor leads. When they're, ideally you want them lugged and bolted together. You want to make sure that when they're lugged, they're properly crimped so that they're not squeezed too tight to cut strands, and it's not loose to promote a high resistance connection. You want to make sure that all the edges are smooth. If there's any sharp burrs on them, you want to file that off before you start taping. Otherwise that stuff's going to wear through that tape and eventually going to cause a problem inside the pecker head and go to ground. Once you've got that all good and clean and tight, make sure the lugs are clean when you put them together. A lot of times when you pull them out, put them back in, they can get dirty. You want to take a rag, wipe them off. They look tarnished, use a little bit of Scotch-Brite on them by hand. Just clean them up. Just, you know, have good connectivity so you don't have a high resistance connection. And then you want to properly tape them. We use a 3-layer method. We start with varnished cambric, a non-adhesive, because then that provides some dielectric strength, a little bit of mechanical strength, but mainly for us, we use it as a release agent. If you just put rubber straight over your lugs and wire, splicing tape, and go to get that back off after it's been in service for a while, you're going to have a heck of a time. It's going to be bonded because it's typically self-vulcanizing tape, which means it like melts itself together. Without that on there, or some other release agent, you're going to have a hard time getting that off of there. If you don't have any cambric tape, you can use your vinyl. Just put that on backwards, just one layer. You don't need a big thick coat of it. Just one layer on there is all you need, and then that provides a release. So we use our varnished cambric, and then we wrap it with Scotch 130C rubber splicing tape. And you want to keep some tension on it like he's doing there to make sure it stretches a little bit, and get that wrapped on there. And then the last layer would be your vinyl tape on top of that. You want to make sure that as you're taping that up, you feel around there. If you can still feel the bolt heads or any edges coming through, you don't have enough tape on yet. Tape's cheap compared to the problem that you're going to have once it blows to ground inside that pecker head. You can make a motor rewind that way, cause all kinds of problems, downtime, which nobody likes. So you want to make sure that it's good and taped. That's just cheap insurance to have plenty of insulation on there. And then wrap it a little bit of vinyl over the top of that just to make sure everything stays good and tight on there. And that's really all you need. And then the advantage of that is when you go to cut that loose, even years later, all you got to do is slice down the two sides in between the leads, and that'll pop off like a cocoon. He'll show you that when he gets that done. But Always remember to keep some tension on that tape as you're wrapping it so it's good and tight on there and it doesn't just unravel on you. You want a little bit of stretch, that'll help it bond better. And then now you've got a well-taped connection. If you want to go ahead and pass that around, you guys can take a look at it, and then at the end when it comes back up, we'll cut it open and show you. Excuse me. But some questions to ask yourself when you're troubleshooting a motor problem. Say you have a motor goes down in a plant and blows a fuse or trips a breaker, trips an overload. You don't want to just reset the breaker or reset the overload or throw another fuse in it without checking out why did this happen. First thing you want to do is, one, has it been in service for a while, running fine and dandy, and all of a sudden something happened, or has this motor just been changed out and we're having problems with? Because that can help you steer you in the right direction to go. If it was recently installed, you could have something like wrong voltage connection in the motor. It might not be connected for the proper voltage. You could have, excuse me, a few other problems. You want to look at the nameplate. If it's recently installed, look at the nameplate of that motor and check your incoming voltage to make sure that you have this thing connected properly. If it's connected properly, then you can go on to some other checks. Make sure your fuses are good. Make sure you have good power coming in from your main, wherever that's coming from, whatever it's feeding at. Check for good phase-to-phase voltage balance. You really don't care about what phase to ground voltage is because the motor doesn't operate on that. It just operates on phase-to-phase voltage. So you want to check that and make sure that that's good. Lock out and tag out before doing any further testing. You've checked your incoming, you know that's good. Now if it's a cross the line motor starter, you can go on the bottom side of the contactor and then check that motor to ground with your megger and see if it's grounded or not. If it's grounded, then the next thing you would want to do is go back to the pecker head and undo your connections there and check, is it the motor, is it the cable, or a combination of both. So we've checked it at the starter and we're 0 megs or a couple megs, it's low. So we go to the pecker head and we're going to open that up and check that there. Now if the motor checks good but the lines check bad, then you know you have a problem in the wire and the pipe somewhere between the motor starter and the controller and the motor itself. If that all checks good and it's just the motor that's checking bad, then obviously you have a problem there. Now as you're doing this and you've checked that motor and it's not grounded, then you can go ahead and check phase-to-phase resistance. That should be equal. I can't tell you what it's going to be because all motors are different size motors, different manufacturer motors are going to have different resistance values phase to phase. But the main thing to keep in mind is that you want equal resistance phase to phase on all 3 legs. Yes, Mike?
Couldn't there be 5% difference between?
No. No. Identical. Within a few tenths of an ohm, you know, depending on the resistance reading you're getting, you're going to be less than 0.5% though. They should be really, really close phase to phase. If not, you have an imbalance in the winding. There's something that's went on in there and that would be the cause for your problem. So at that point in time, you'd want to change that motor out, put your spare in if you have one. If not, you have to just get it repaired and back as soon as you can. But yes. So now if your phase-to-phase balance is off, like you said, that's a sign that you have a problem in the motor. A lot of times you can tell if there's an electrical problem in the motor, when you open that pecker head up, you're going to smell a burnt smell. If any of you have ever smelled a burnt electrical smell before, it's a one-of-a-kind smell and you know that. You open that pecker head up, it's like, oh yeah, okay, that's where my problem is. You still want to isolate and find out, okay, was that smell from a wire in the pipe that went bad, or is that from the motor itself? So you want to isolate and figure out which one is which. You wouldn't want to pull the motor, put your spare in, go to connect it up and find you got the same problem because you still have a bad wire in the pipe. And you could have eliminated changing the motor out by doing that first. Excuse me. And then he'll show you when you go ahead and time to pull that motor out, if you just slice between the 2 conductors up through there on each side, that'll come off of there, kind of like taking a cocoon off. You want to make sure you use tape. I've seen a lot of things out in the field. I've seen paper wrapped around leads with a little bit of vinyl over it. I've seen shop rags wrapped around with some vinyl over it. Really, you know, I guess the guy was in a pinch or something, but see, and that just comes off nice then. You're not fighting it. Boom, boom, and in no time you're done with it. So always make sure that your voltage is balanced. Your voltage phase to phase should be balanced within 1%. But back to your initial problem, that motor tripped out, you're not sure why. If you meg it, and it megs good at the bottom of the controller, now if it's running off a VFD, you want to take those motor leads off that VFD before you meg it. You don't want to meg a drive. They typically don't like that. Depends on the type of megger. Some sources say a battery operated electronic megger is okay. Others say no. I've always gone with don't meg a drive on the load side or line side for that matter. You don't want to meg a drive because there's electronic components in there that aren't going to take very kindly to that. You can do damage just by megging the drive. So if it's on a VFD, take your line lead or your motor leads off the bottom side of the drive, meg that, make sure that it's not grounded. Typically for a 230 or 480 volt system, ideally you want to see 100 meg ohms or better. I've seen a lot of things run lower than that. You know, they could run at even 10 megs, but as it starts heading down and your lower meg ohm readings, your trouble is brewing somewhere. So you want to find that out and take care of that problem. Motors need maintenance just like anything else, your car or anything. They won't just go in there and run forever, so sooner or later they're going to have to be pulled and serviced. But look for that sign of trouble. Why did that breaker blow? Why did the overload trip? Why did the fuse blow? Whatever that reason is, look for signs of overheated wires in your control panel. If your motor's megging good and your phase-to-phase resistance is good and you don't see any other reasons for that to be an issue, check the load. See, is the motor sound? And what I mean by that is, if you grab a hold of that shaft, can you move it up and down or in and out? Typically, electric motor, you don't want any movement in the shaft other than rotational movement. It shouldn't have radial or axial play, with the exception of if it has sleeve bearings in it, you are going to have axial play in the motor shaft. Otherwise, it'll bind up. But if it's a ball bearing or roller bearing motor, anything other than a sleeve bearing, you don't want play in it. So check and see if you've got play. Check and see, does it turn freely? If you can't turn it freely, you might need to uncouple it from the load, or if it's a belted load, take the belts off. See, where is the problem lie? Is it the load that is having an issue with rotation, or is it the motor itself? You get that load uncoupled and you can move that shaft around, then you know the bearings are shot, you've got some internal problem in the motor, you need to go ahead and pull that. If left continue to run, it can get bad enough where then the rotor will drag on the iron and overheat the winding and cause it to be a rewind. So you want to pull it before it gets to that point. That's another thing where preventive maintenance things by doing vibration analysis and routine monitoring to stay ahead of the game on that, kind of build a trend and history of what kind of problems you're having with that motor. Are the bearings in bad shape? Those things. If you have mechanical problems, then you need to change that motor out and put in something without mechanical problems. So if you've checked that and you don't have mechanical problems, the load is okay, etc., then you can go ahead and run the motor. Replace that fuse. You've determined that it's not grounded. You've got good phase resistance. You don't really find a reason for that, then go ahead and try it. But 9 times out of 10, when you do these steps, you're going to find there's an issue somewhere. You want to correct that then before just throwing the switch back on and watching fire fly out of the thing. Once you get it running, then check with your amp meter and see, do we have balanced current? Is the current within nameplate specs? Always look at your nameplate. Some people ask about service factor. Service factor is basically what you can overload the motor by at normal operating conditions. What that is, if it's 460 volt rated motor with a 1.15 service factor, if it's running at 460 volts, you can multiply the current, say it's a 10 amp motor, by 1.15, you can go 15% over then on that motor, on your current, at rated voltage. If you're at 480 volts and it's nameplated for 460, you've already used up some of your service factor, so you can't take that into account anymore. You can't overload it. What you're going to do then is you're going to overheat the windings and shorten its life. Sometimes you'll also have a faulty breaker. A breaker might be tripping prematurely. You're checking the current on the motor, this breaker keeps tripping. Your current is within nameplate specs and well below the breaker. You can't find another cause for that. The measured current at the breaker is below its rating, but it's still tripping. You could have a faulty breaker. They do eventually wear and have to be replaced. Also, you want to check for voltage balance once your motor is running. Check if you have an across the line starter. It's good practice to check your contacts by going across L1 and L2, or I mean the line and load side of each leg across that contactor, and do a volt drop check. That should be within millivolts of each other. Top to bottom, you shouldn't read voltage. Basically, it's just like a straight piece of wire. If you're reading a voltage in there, then you have a high resistance connection, which is going to cause heating there, going to cause unbalanced voltage and unbalanced current at the motor, which is going to lead to shortened life. Yes?
Yeah, service factor. So a rule of thumb for like if you got a 460 volt motor, it's only running at say 440. Or is there some rule of thumb for trade-off between service factor and voltage?
Yes and no. There's your power company, the utility, is supposed to deliver you power within 10% of nominal voltage. So if it's a 480 volt service, they can go plus or minus 10%. Usually they're not that high. It's usually closer to 5. Sometimes it's less than that, but it is not uncommon to find motors running either above or below rated voltage. And it's just one of those things. You're gonna, at less voltage, you're gonna have lower performance. It's not gonna develop the torque that it would at rated voltage. It is gonna overheat because you're not developing the torque if the motor is fully loaded. Now, if you have a 25 horse motor and it's only really needs a 20, you're probably not gonna notice a problem. But if the motor is really closely matched to the load, then you're gonna start to see some issues.
So you have a rule of thumb for 1% difference on voltage, take away 10% of the service factor, or something like that?
No, not really. Anyone else have any other questions on AC motor troubleshooting? Basically, approximately, if it's an unloaded motor that's not driving a load, running at nameplate voltage, then you should be approximately 1/3 of the nameplate full load amps. That's just a basic rule of thumb. Now, there are exceptions to that. Lower speed motors, say 1200 RPM and below, they typically run closer to half, or sometimes if you get certain motors, they can even run at nameplate current, no load. Sometimes even a little bit more on like a 900 RPM motor. They'll run a little bit higher, but once you load them, because of slip, they will come into nameplate current. Main thing is you're looking for balanced, and most of the time they should be below nameplate amps, typically about 1/3. All that's good, then you can put your belting back on or reconnect your coupling, and then as long as your motor ran good unloaded, go ahead and fire it up, run it again, check your current, make sure you're within full load amperage. If you have any kind of trending information on them, then that helps you better analyze problems that come up. If you have over time taken amp readings on that motor when things seem to be running normally, and you know that during normal process it runs at nameplate amps, or maybe it's rated for 30 amps and it's only ever runs about 25. If you periodically check that on routine maintenance type things, you can see as that current starts going up over time, then that's a good indication that you might have mechanical issues going on, causing more of a load, therefore more current on the motor, which is going to increase the heat, shorten the life of the windings, etc. So just all good troubleshooting tools to occasionally take a look at these things. Listen to your motors. They'll tell you a lot. If you're familiar with that motor running normally, it sounds a certain way. Later on, as problems develop, you walk by that motor, you know, it could be running along, nobody's complaining of a problem. You're walking down the aisle, you hear, well, that don't sound right. Go investigate that. Most likely, if you're noticing that something's different, something probably is. It could be good or it could be bad. You want to check on totally enclosed fan cooled motors that your cooling vents on the back side of the motor for your fan shroud, all those openings are open. Once they get packed full of debris, you know, some places are cleaner than others. They get a lot of stuff sucked into them, these cottonwood seeds and dirt and debris, grease, oil gets on there. They'll pack that up. That restricts the air inlet to the fan. Therefore, it's going to reduce the cooling effectiveness of that fan on that motor, causing it to run hot and shorten the life. Same thing with the cooling fins on motors. I don't see any around here setting outright. Well, in back of us there's some, but the cooling fins on motors, which you guys are probably all familiar with, you want to keep those clean too. Those get plugged up. That's just an insulating blanket, because all those fins are a heat sink. And if you cover that heat sink up and start insulating it, it's not going to cool as efficiently as it should. And therefore, it can lead to increased heat and shorten life of that motor. And if you've done everything else, you've checked everything, and you just can't find a problem, it's still having issues, then call, we'll come out on a service call and help you figure out the problem. Going into the next section, basically there's a lot of reference material in here we won't go into a lot of detail on, but it gives you some information on suffixes to NEMA frames, what these letters and designations mean on frame sizes. Metric motors are a little bit differently, like for example a C on that mounting. If it's a 215T C motor, that means it's a 215T frame motor with a C flange on it for coupling up to something. If it was a metric motor, that would be a B14. Similarly, if it was a TD, that's a D flange. That's a little bit bigger flange with open holes, not threaded, to bolt up to something. That would be a B5 in a metric frame. Always look at your nameplate. Whenever you need to replace a motor, look at the nameplate and look at the motor. When at all possible, if you're going to call in and order a motor, if you can take a picture of it with your phone and send that to us along with it, that shows the shaft and the lead box, that will help us to make sure that something didn't get changed in the field at one point in time that never got reflected on the nameplate. Sometimes we'll need a motor for a customer. The customer needs a C or a D flange motor. The factory doesn't have any in stock, but they have a standard T-frame motor and they have D or C flange kits in stock. We'll get those in. We'll change that here in the shop, but then we also need to change the nameplate to reflect that. Sometimes that doesn't happen, whether by us or somebody else. You can get a nameplate that says one thing, but the motor is really another. If you strictly order it off of the nameplate, and it's especially a problem if you're hot for it, we get you what you asked for, and then you get it in and go, there's no flange on this. Well, if it wasn't on a nameplate, we can't do anything about that. So if you take a picture and send that to us, that just helps kind of minimize that. When you're looking at the motor, the relationship of the lead box to the shaft coming out makes a difference. I'm sure you guys have seen most motors out there are what they consider F1 mount. If you're looking at the lead box side of the motor, the shaft exits on the right. If it's exiting on the left, then it's F2. Those are typically not stocked. Sometimes they are, but they can a lot of times be converted here at the shop to make it the right setup for you, whether it's F1 or F2, but we want to make sure that you get the right motor the first time. So the more information we have, the better. Another thing is, if at all possible, do not remove the nameplate from the motor. Most times, you know, somebody will ask, we need the nameplate information. Somebody will go out there, well, it's kind of up underneath a table or something, it's hard to get to, so they just chisel it off. Good intentions. I got the information from my boss, he needed this information. 99% of the time, that nameplate never makes it back to the motor. Down the road, you have a problem with that motor, you send it in, we get it in the shop, and there's no nameplate on it, it's burned up, and it makes it real difficult to determine exactly what you had here. We can determine the frame size by taking some measurements on it before we disassemble it, but that's only part of the picture. We also need to know the RPM, the horsepower, and the design of the motor. Like if it's a Design D, a high slip press motor, that's going to be a lot different than a regular off-the-shelf motor. Design Ds, some of them are stocked, but a lot of them are not. They're made to put up with that high slip in a stalling application like a press or something like that, or oil rigs, etc. So just really do everything you can not to take that nameplate off. You can get your smartphone up there and take a picture of the nameplate, you're much better off, because then that information stays with that motor. As you flip through here, the next section is we've got some terminal markings and connections for you to help you figure things out. A lot of times connections are on the nameplate. The nameplate is a wealth of information for your motors. It should tell you everything about that motor. Sometimes they'll have a separate connection nameplate, sometimes it'll be a sticker inside a lead box, but all that information is important and makes a difference when you're troubleshooting a motor, whether you're replacing a motor. Always refer to the nameplate. Some of this information that's in here as far as the connections are some of the more oddball stuff that you don't see out there much, but if you need it, that reference material is good to be able to rely on and come back to. Next section is dealing with the effects of high, low, and unbalanced voltage, as you were asking earlier, Donald, is it? This kind of gives a little bit more in depth on that. It doesn't really talk about the effects of that versus service factor, but it does detail problems that you're going to run into by having unbalanced voltage. Typically you want to be within 1%. Anything outside that, you're going to have uneven heating because you've got now uneven voltage. So some phases are having higher current than others, so now we got uneven heating in the motor, and it just comes into performance issues and basically shortening the life of that winding. You want to do everything we can to keep that motor protected and running properly as long as we can. Next section is on DC motors. We've got a cutaway view of the DC motors. There's a large field frame down there for a DC motor that you guys can look at. How many of you guys have DC motors in your plants? Okay, a fair amount of you. You know those, you need to do routine maintenance on them. You need to make sure that you check periodically the brush condition. Don't let the brushes get too short. Inspect your commutators for signs of arcing. It's a good idea to be able to have a Lexan cover or some other clear cover on one side or the other of the comm end of the motor, because then if it starts arcing, you have issues, you can see that before it starts coming out the vents. Usually by the time you can see it past a vent, it's way too late. But if you can see some arcing going on in there, then you know that you need to address that and see what the problem is causing that arcing. It could be a buildup of filth on the comm, it could be the brushes are short, it could be your spring tension is weak and just not performing properly. There again, the DC nameplate gives you a lot of information on there. Sometimes they give you resistance values of what your shunt field should be resistance-wise. Sometimes they do not. But they give you voltage, they give you current. If it says max amps, that's your cold amps. That's your highest amps are going to be when your fields are cold. As it warms up, resistance increases and the current decreases because of that. So you always want to look at that nameplate and compare what is my voltage versus what it's supposed to be on the nameplate. They give you a little bit more information on temperatures and stuff on this DC nameplate information here. The next section has terminal markings and connections for DC motors. Basically you got three basic types of motors. You have a series motor, which is a traction motor like what's running that train down the track. The field windings and the armature windings are in series with each other. They have a lot of torque, but they have very poor speed regulation. You cannot run a series motor at rated voltage without a load on it, or it will over accelerate and centrifugally fly apart. So if you got one on the bench, whether it's a starter motor, a forklift hydraulic motor or something, if you got it on the bench and want to do some testing on it, just be very cautious about that. You do not want to put nameplate voltage on. If it's rated for 36 volts, if you want to try to check something, you can maybe run it off a battery charger on 12 volts, but watch that speed. If you put full battery voltage on that thing, it will run away in no time at all, and it won't be pretty. You'll ruin that motor and possibly cause yourself and others harm. Shunt motor is one of the most common types. They have very good speed regulation. There's many turns of fine wire in your shunt fields that are separately powered, and then your armature and interpole circuit have a separate power source. Good speed regulation, they do good work. Then there's a compound motor, and that's kind of the best of both worlds. You have a series field that's wound around the shunt field, so you have that torque, and there, as the name implies, the series field is in series with the armature circuit. So as you get more load on the armature and the current goes up, that also increases the current in the series field, which is around your shunt field. It strengthens the field and gives you more torque. And so you get kind of the best of both worlds there. As the load increases, you can get a little bit more torque out of it with a compound motor. There's more pieces in it, but you do have that. Excuse me. The next section is on brush holders and performance of carbon brushes. That's something that, like I said, I can't stress enough. You need to make sure that with brushes, you don't let them get too short. There is something called a shunt. That's the leads that come into the back side of the brush, opposite of the end of the com is riding on. Those are set down in there a ways. It's hard to tell how far out down they are, but if you let your brush wear down too far and that shunt gets into the com, you're going to start digging grooves in the com, rolling the edges of it over. Now you got shorts in the com and time to be pulled in service. So you want to stay ahead of that game, and when you see your brushes starting to get short, change those out before you get to the point where the shunts are down in the com. If you notice any heavy grooving in the com or where it's starting to smear over from bar to bar, then you want to pull that and service it, put your spare in, and get that com serviced before you have major problems. If you let it go too long, you can end up having costly rewinds and extended downtimes. So this section here just tells you a little bit more about brushes. They need to be, when you're changing brushes out, they need to be the proper grade and size. If you have brushes that don't quite fit right, if they're too sloppy in there where they're moving around, you really don't want to use those, because now you've got a couple things going. They're moving around in the brush holder and going to cause excess wear. On top of that, you're not going across as many bars as it's designed to if the brush isn't full width, and so you're going to have performance problems because now you don't have all the armature winding in the circuit even though you think you do. So it's just very important to have a proper fit. They need to slide in the brush holder nicely, but you shouldn't be able to rock them around. I mean, a little bit, because you're going to have clearance because of thermal expansion. They can't be too tight. So try not to substitute brushes if at all possible. You want to make sure the grade's the same. And that is basically the color of the brush. So if you go by the same number and make sure you replace it with the same number, then you're in good shape. You won't have those issues. But DC motors are just high maintenance motors, because you've got that carbon that's wearing from those brushes. That carbon's going somewhere. It's going inside the motor. You can vacuum them out occasionally. Some people blow them out, but the problem with blowing them out, you will get some carbon out, but you're also going to pack some of it into nooks and crannies that you'll never get it out of. So best case scenario is to vacuum out whenever possible, and make sure there again that your blower, most DC motors are blower cooled. You want to make sure you keep that filter clean so it has proper ventilation and cooling. If you don't have proper cooling, you're going to have problems just like with the AC motor. You're going to have overheating problems and shortened insulation and winding life, and lead to premature failures, and you're going to have to just do something about that sooner than later. So if you're proactive about it and stay up on your maintenance of your filters, change those regularly. A lot of people will put some filter pre-wrap around it, that foam, blue foam stuff that we've all seen out there. You can change that as needed and lessen the frequency of actually changing your other filter out. But there again, you want to keep good air filtration and proper airflow in that motor. And the last section is basically on troubleshooting DC motors in the field. There again, as with any type of electrical work, you want to make sure that you lock out and tag out before getting your hands in on something. You have a problem, the motor's been running along fine, all of a sudden the operator experiences either shut down on its own, tripped a breaker, tripped an overload circuit, something happened and stopped that motor running, or it's just running erratically and they're not sure why, and they bring it to your attention. Well, if you can observe what's going on safely, do so you know exactly what the operator is talking about. Then power the thing down, lock it out, tag it out, and always verify your voltage. Don't just trust that when I turned off that three-phase disconnect, or turned off the power supply, that everything's dead. You want to turn it off, lock it out, and then measure it. Measure it with your voltmeter and make sure that that is actually powered off before sticking your hands in there, because you can't see electricity, but you sure can feel it. And most of us have gotten across some form of voltage at one time or another and know what I'm talking about. You get across it in the wrong circumstances and that'll be the last thing you ever do. So I can't stress enough the importance of making sure it's locked out, tagged out, and you verified that it's off. A good test to do is what they consider a live dead live test. You're going to verify that your power is off. Use that voltmeter on something you know is turned on first and it's reading voltage. Make sure you have voltage on your meter. That tells you the integrity of the leads. You can do an ohm test too, but you want to verify you got power coming in. You check it on the dead circuit and it is off. Then check it again to make sure that you're still reading voltage. Something didn't happen, because electrical circuits can fail and lead to a problem. You thought it was turned off, you trusted your meter, but you only checked it on one thing, so it lied to you, and then you ended up getting bit and wondered why. So if you do that, that will minimize the chances of that happening. There's no such thing as totally eliminating any chance, but the more we can reduce that risk and use our tools and experience to make sure that we don't get in a situation that's going to cause us or others harm, the better off you're going to be. So now that we got it locked out and tagged out, on a DC motor we want to pull the covers at the comm end and look in there at the commutator and the brushes. Do I have any short brushes? Check all your brushes and make sure none of them have got down into the comm with the shunts and cause problems there. What does the commutator look like? Are the bars nice and clean? Are they pitted? Does it look arced up? If there's signs of arcing in there, then you have an issue somewhere. Most likely, if it's arced up on the comm, you're going to have to pull that out and bring it in for service. What you want to do is check your voltage against the nameplate voltage. If your shunt field voltage is 300 volts, you want to check your power supply then and see, do I have 300 volts going on there, or is it less? If it's less, what's the cause? Inspect your circuits. You can go back to the controller. Most controllers are, some have, I won't say most, some have output contactors, some don't. So you want to take your shunt field leads and your armature leads off at the controller and meg them from there on out. You should not be grounded. You want to have, you know, ideally 100 meg ohms or more on any of those circuits to ground. If you have less than that, it just depends. Some armature circuits and DC field circuits I've seen run as low as a couple meg ohms. That's really, really close to having a major event and the thing going to ground, and it's going to cost you a lot more to have it fixed then than if it's just a cleanup and bearing change. As that carbon packs up in there over time, you're going to lead to insulation going to ground. That's part of a brush ring, stabilizer ring that was on a DC motor, and there was enough accumulation of carbon tracking that actually started arcing across there and ended up catching on fire. So just cleanliness inside the motor. If you open that motor up and it's really, really filthy, it probably should be pulled in service, because DC motors just are a lot more in need of that than an AC motor, just because of the nature of the beast. You've got, any time you have carbon brushes or brushes of any type in a motor, whether it's a wound rotor motor, synchronous motor, anytime you have brushes, you're going to generate the byproduct of carbon going into that motor. So those are more prone to problems with eventually going to ground because of an accumulation of dirt and carbon. Especially when it gets hot in the summertime, you get the heat and humidity, it just all kind of goos together and then creates paths to ground. So we've pulled our leads off of the armature and field leads off of the controller. Make sure they're marked first so you get them back on in the right place, and then meg them to ground. If they're not grounded and your comm doesn't look bad, you know, you have good commutation looking, it's kind of a chocolatey brown color, there's no signs of arcing on it, then go ahead and excuse me, look for other signs of problems. Same thing with the AC motor. You want to check for mechanical problems. Can you rotate that shaft freely? Is there play in it? If you have play in it or you can't rotate it freely, you need to determine, is it the load or the motor, just like with the AC motor. If it's in the load, then you need to address that. If it's the motor, you need to address that end. If it rotates freely and you can't find other issues, then it's safe to go ahead and power it back up, and then just double check your field voltage, check your field current. It should be within nameplate. If the voltage is low, it's a 300 volt field, and you're only running about 250 volts on it, for whatever reason, whether your controller, your field power supply is acting up, lower field voltage will lead to increased speed but also less torque. So you won't have as much torque out of a motor. On your DC motor, when you're looking at that nameplate, it'll show sometimes two different RPMs. You might have 1750 and 2500. The motor might be rated for 500 volt armature and a 300 volt fields. Well, that tells you that that first speed, the lower speed, that is your what they consider base speed. When you're at nameplate voltage on your fields and your armature circuit, it would run at that speed. That higher speed is with field weakening, and they'll usually tell you minimum field current of what you can weaken that field down to. They do that to get more speed out of for process, but what you trade off on is torque. As you increase the speed by lowering your field current, you lose torque, because the torque is built through your field strength. If your voltage is over, nameplate voltage on your shunt fields, then it's going to be a little torqueier, but you're going to create excess heat and you're going to prematurely burn the fields up. So you want to make sure that that's matched properly. Check your current. If your current is good on your fields and you got good voltage supply, then you can go ahead and energize it and check your DC motor while it's running. Look at your field or your armature current and see, is it within nameplate specs or not? Does it run smoothly, or is it hunting around for speed? If you have Tack feedback on it, some DC motors have Tack feedback, some of them don't. If you have Tack feedback and your motor is not running a constant speed, you very likely have a problem in that Tack feedback circuit. Your Tack could have, depending on whether it's an AC or a DC Tack, if it's a DC Tack, it's got brushes in it, and your brushes could be short and worn, not giving you a good signal back to the motor. So you want to check that. You could just have a problem in the Tack. Could also be another issue, but those are the things that you want to check if it's hunting, and look for signs of not good Tack feedback. If everything looks good back there, then you can check where your where your Tack supply comes back into the drive, and check, are you getting a steady voltage or not? If your voltage is steady but it's still hunting around, then it's something to do with the drive. If that voltage is fluctuating, then you probably have a Tack problem. Although if the motor is still hunting and not running at a given speed, a steady speed, you are going to have varying voltage, so you need to keep that in mind. If you see signs of something doesn't look right in your DC motor, your fields have checked good, it's not grounded, with it uncoupled from the load, you can energize the shunt fields and leave your armature leads off of the drive. And you use caution with this, because you don't want to have any power going to the armature circuit to cause rotation. Well, with the shunt fields powered up and nothing connected to your armature leads, if you rotate that shaft, not fast, but just slowly rotate that shaft a full turn, if it rotates evenly and doesn't have tight and loose spots, then the commutator and the armature is most likely not shorted. If you feel tight and loose spots in there, that is indication of shorts in either the armature or the commutator. Either way, if you experience that, then that motor needs to be pulled and serviced. You need to put your spare in at that point in time. Nameplates, like I say, are very just key. They give all the information that you need on there to tell you what that motor should be doing. Check your RPM. If you can get a tack on it, sometimes you can't get a tack on the shaft, a contact tack, but you can usually find a place to use a photo tack. If you're using a photo tack on a shiny surface, typically you have to put some reflective tape on that comes with your tack. You want to put down a layer of just some black tape first, a little bit of vinyl tape on that shaft, because if you have that reflective tape on a shiny shaft, you'll get a false reading. So if you put just a couple layers of vinyl tape down first and then put your reflective tape on, you'll have a more accurate reading of your speed. So if you have nameplate rated voltage on the fields and the armature, it should run nameplate RPM within a couple of percent. Just that varies with load. So If all that checks out good, go ahead and run it. If your current is below nameplate, you have proper voltage and current on your shunt fields, and the less, typically you're going to have on an armature circuit, if it's not driving a load, you're going to have a very low percentage of full nameplate amps on your DC motor, because it doesn't take much to run that motor at no load conditions. So don't be alarmed that it's way lower than the nameplate is. You want to be alarmed if it's higher. You also want to look for signs of arcing when you do run that motor. Make sure if everything looks good, then you can go ahead and couple it up to your load and run the load. Check your current against nameplate and make sure that you're within nameplate current readings and not over. Look for signs of arcing at that time. If you don't have any arcing, then it was probably a fluke thing that happened that caused that to trip. But most of the time when you have a trip like that, it's because there's something wrong. We just need to dig and find that problem. If you go through everything and you still can't figure it out, it's still not running right for you, you're still having issues, give us a call and we'll come out there on a service call and help you figure out the problem. There again, cleanliness of the outside of the motor is also important on DC motors just like it is on AC. Even if it doesn't have cooling fins on it, any accumulation of buildup on the outside of the motor is going to like insulate. It's like wrapping a blanket around the thing and retain heat. You want to try to keep it clean. You know, it doesn't have to be spotless, but you want to keep the accumulations from building up on that to make sure that it has proper heat transfer and cooling. Anytime you have a blower on a DC motor, you're going to have a blower at one end, sometimes on the comm end, sometimes on the drive end. But you're going to have the opposite end of the blower should be louvered covers, at least 2 of them, sometimes 3 or even 4. You want to make sure you have good airflow coming out of that motor. Anytime you send a DC motor in for repair, send the blower in with it. You don't want to have your motor rebuilt, go to put it in, put your old blower back on that's got oil dripping off the fan blade and a bunch of filth in there. You're going to pump that stuff right back into that rebuilt motor. You want to always put a rebuilt blower back on your motor, if at all possible. If you don't have a spare, then you should make us aware of that at that time. We can supply you with a spare so that you'll have one for each motor. It's just very important to keep it clean and as much air flowing through that as possible. When you change that blower out, you want to make sure that it's running the right way. Most of them have direction arrows on them. You want to make sure it's running the right way because it will not move the proper volume of air if it's running in reverse. It's just a typical squirrel cage blower on most of them. But you want to make sure that you have proper rotation so that you have proper airflow. Well, I think that's basically, that pretty much covers everything there. We do have electrical and mechanical engineering pocket handbooks. You guys probably saw some when you came in. This is an older version, so the cover looks a little bit different. But these are 2 very good sources of information. They give you wire size. They have also motor connections in them as well. They have some lubrication recommendations, conversion charts, bearing fits. Just a lot of good information inside those things that are just valuable references to you. They fit in your pocket and are handy to have on hand. And there again, if any time you guys run into a problem out in the field, say you're checking something and something just doesn't seem right to you, you got a question, give us a call. We'll try to help you out over the phone and answer, help you troubleshoot over the phone. Sometimes it doesn't require a service call. Sometimes there's something that, you can tell us the symptoms, you can tell us what you checked. We'll ask you some questions. There might be something that we come up with to tell you to check that you didn't think of. Those are all just good tools to use. Don't be afraid to pick up the phone and give us a call. There's nothing wrong with asking for help. We all need to know when to ask for help. There's things that we run into that, boy, I haven't run into that before. I'm not sure what to do. Let's find someone that can answer that question. And if you call us up and we don't have an answer for that question right at the time, we'll find out and call you back. So I guess with that, if there's no other questions, that concludes this seminar, and I hope you guys got something out of it.